We shall give here a second demonstration of the fundamental proposition enunciated on page 56, and present this proposition under a more general form than the one already given. When a gaseous fluid is rapidly compressed, its temperature rises. It falls, on the contrary, when it is rapidly dilated. This is one of the facts best demonstrated by experiment. We will take it for the basis of our demonstration. Footnote. Note 13, Appendix B. End footnote. If, when the temperature of a gas has been raised by compression, we wish to reduce it to its former temperature without subjecting its volume to new changes, some of its caloric must be removed. This caloric might have been removed in proportion as pressure was applied, so that the temperature of the gas would remain constant. Similarly, if the gas is rarefied, we can avoid lowering the temperature by supplying it with a certain quantity of caloric. Let us call the caloric employed at such times. When no change of temperature occurs, caloric due to change of volume. This denomination does not indicate that the caloric appertains to the volume. It does not appertain to it any more than to pressure, and might as well be called caloric due to the change of pressure. We do not know what laws it follows relative to the variations of volume. It is possible that its quantity changes either with the nature of the gas, its density, or its temperature. Experiment has taught us nothing on this subject. It has only shown us that this caloric is developed in greater or less quantity by the compression of the elastic fluids. This preliminary idea being established, let us imagine an elastic fluid, atmospheric air, for example, shut up in a cylindrical vessel, A, B, C, D. Figure 1, provided with a movable diaphragm or piston, CD. Let there be also two bodies, A and B, kept each at a constant temperature, that of A being higher than that of B. Let us picture to ourselves now the series of operations which are to be described. 1. Contact of the body A with the air enclosed in the space A, B, C, D, or with the wall of this space, a wall that we will suppose to transmit the caloric readily. The air becomes by such contact of the same temperature as the body A. CD is the actual position of the piston. 2. The piston gradually rises and takes the position of EF. The body A is all the time in contact with the air, which is thus kept at a constant temperature during the rarefaction. The body A furnishes the caloric necessary to keep the temperature constant. 3. The body A is removed, and the air is then no longer in contact with any body capable of furnishing it with caloric. The piston meanwhile continues to move, and passes from the position EF to the position GH. The air is rarefied without receiving caloric, and its temperature falls. Let us imagine that it falls thus till it becomes equal to that of the body B. At this instant, the piston stops, remaining at the position GH. 4. The air is placed in contact with the body B. It is compressed by the return of the piston as it is moved from the position GH to the position CD. This air remains, however, at a constant temperature because of its contact with the body B, to which it yields its caloric. 5. The body B is removed and the compression of the air is continued, which being then isolated, its temperature rises. The compression is continued till the air acquires the temperature of the body A. The piston passes during this time from the position CD to the position IK. 6. The air is again placed in contact with the body A. The piston returns from the position IK to the position EF. The temperature remains unchanged. 7. The step described under number 3 is renewed. Then successively the steps 4, 5, 6, 3, 4, 5, 6, 3, 4, 5, and so on. In these various operations, the piston is subject to an effort of greater or less magnitude, exerted by the air enclosed in the cylinder. The elastic force of this air varies as much by reason of the changes in volume as of changes of temperature. But it should be remarked that with equal volumes, that is, with the similar positions of the piston, the temperature is higher during the movements of dilatation than during the movements of compression. During the former, the elastic force of the air is found to be greater, and consequently the quantity of motive power produced by the movements of dilatation is more considerable than that consumed to produce the movements of compression. Thus we should obtain an excess of motive power, an excess which we could employ for any purpose whatever. The air, then, has served as a heat engine. We have, in fact, employed it in the most advantageous manner possible, for no useless re-establishment of equilibrium has been effected in the caloric. All the above described operations may be executed in an inverse sense and order. Let us imagine that, after the 6th period, that is to say, the piston having arrived at the position EF, we cause it to return to the position IK, and that at the same time we keep the air in contact with the body A. The caloric furnished by this body during the 6th period would return to its source, that is, to the body A, and the conditions would then become precisely the same as they were at the end of the 5th period. If now we take away the body A, and if we cause the piston to move from EF to CD, the temperature of the air will diminish as many degrees as it increased during the 5th period, and will become that of the body B. We may evidently continue a series of operations, the inverse of those already described. It is only necessary, under the same circumstances, to execute for each period a movement of dilatation instead of a movement of compression, and reciprocally. The result of these first operations has been the production of a certain quantity of motive power, and the removal of caloric from the body A to the body B. The result of the inverse operations is the consumption of the motive power produced, and the return of the caloric from the body B to the body A. so that these two series of operations annul each other, after a fashion, one neutralizing the other. The impossibility of making the caloric produce a greater quantity of motive power than that which we obtained from it by our first series of operations is now easily proved. It is demonstrated by reasoning very similar to that employed at page 56. The reasoning will here be even more exact. The air which we have used to develop the motive power is restored at the end of each cycle of operations exactly to the state in which it was at first found. While, as we have already remarked, this would not be precisely the case with the vapor of water. Footnote. We tacitly assume in our demonstration that when a body has experienced any changes, and when after a certain number of transformation it returns to precisely its original state, that is, to that state considered in respect to density, to temperature, to mode of aggregation, let us suppose, I say, that this body is found to contain the same quantity of heat that it contained at first, or else that the quantities of heat absorbed or set free in these different transformations are exactly compensated. This fact has never been called in question. It was first admitted without reflection, and verified afterwards in many cases by experiments with the calorimeter. To deny it would be to overthrow the whole theory of heat to which it serves as a basis. For the rest, we may say in passing, the main principles on which the theory of heat rests require the most careful examination. Many experimental facts appear almost inexplicable in the present state of this theory. End footnote. We have chosen atmospheric air as the instrument which should develop the motive power of heat, but it is evident that the reasoning would have been the same for all other gaseous substances, and even for all other bodies susceptible of change of temperature through successive contractions and dilatations, which comprehends all natural substances, or at least all those which are adapted to realize the motive power of heat. Thus we are led to establish this general proposition. The motive power of heat is independent of the agents employed to realize it. Its quantity is fixed solely by the temperatures of the bodies between which is effected, finally, the transfer of the caloric. We must understand here that each of the methods of developing motive power attains the perfection of which it is susceptible. This condition is found to be fulfilled if, as we remarked above, there is produced in the body no other change of temperature than that due to change of volume, or, what is the same thing in other words, if there is no contact between bodies of sensibly different temperatures. Different methods of realizing motive power may be taken, as in the employment of different substances, or in the use of the same substance in two different states, for example, of a gas at two different densities. This leads us naturally to those interesting researches on the aeriform fluids, researches which lead us also to new results in regard to the motive power of heat, and give us the means of verifying, in some particular cases, the fundamental proposition above stated. Footnote. We will suppose, in what follows, the reader to be au courant with the later progress of modern physics in regard to gaseous substances and heat. End footnote. We readily see that our demonstration would have been simplified by supposing the temperatures of the bodies A and B to differ very little. then the movements of the piston being slight during the periods 3 and 5, these periods might have been suppressed without influencing sensibly the production of motive power. A very little change of volume should suffice, in fact, to produce a very slight change of temperature, and this slight change of volume may be neglected in presence of that of the periods 4 and 6, of which the extent is unlimited. If we suppress periods 3 and 5 in the series of operations above described, it is reduced to the following. 1. Contact of the gas confined in A, B, C, D, figure 2, with the body A. Passage of the piston from CD to EF. 2. Removal of the body A. Contact of the gas confined in ABEF with the body B. Return of the piston from EF to CD. Removal of the body B. Contact of the gas with the body A. Passage of the piston from CD to EF, that is, repetition of the first period, and so on. The motive power resulting from the ensemble of operations 1 and 2 will evidently be the difference between that which is produced by the expansion of the gas while it is at the temperature of the body A, and that which is consumed to compress this gas while it is at the temperature of the body B. Let us suppose that operations 1 and 2 be performed on two gases of different chemical natures, but under the same pressure, under atmospheric pressure, for example. These two gases will behave exactly alike under the same circumstances. That is, their expansive forces, originally equal, will remain always equal, whatever may be the variations of volume and of temperature, provided these variations are the same in both. This results obviously from the laws of Mariotte and Messieurs Gay-Lussac and Dalton, laws common to all elastic fluids, and in virtue of which the same relations exist for all these fluids between the volume, the expansive force, and the temperature. Since two different gases at the same temperature and under the same pressure should behave alike under the same circumstances, if we subjected them both to the operations above described, they should give rise to equal quantities of motive power. Now this implies, according to the fundamental proposition that we have established, the employment of two equal quantities of caloric. That is, it implies that the quantity of caloric transferred from the body A to the body B is the same, whichever gas is used. The quantity of caloric transferred from the body A to the body B is evidently that which is absorbed by the gas in its expansion of volume, or that which this gas relinquishes during compression. We are led then to establish the following proposition. When a gas passes without change of temperature from one definite volume and pressure to another volume and another pressure equally definite, the quantity of caloric absorbed or relinquished is always the same, whatever may be the nature of the gas chosen as the subject of the experiment. Take, for example, 1 liter of air at the temperature of 100 degrees and under the pressure of 1 atmosphere. If we double the volume of this air and wish to maintain it at the temperature of 100 degrees, a certain quantity of heat must be supplied to it. Now, this quantity will be precisely the same if, instead of operating on the air, we operate upon carbonic acid gas, upon nitrogen, upon hydrogen, upon vapor of water, or of alcohol. That is, if we double the volume of 1 liter of these gases, taken at the temperature of 100 degrees and under atmospheric pressure. It will be the same thing in the inverse sense if, instead of doubling the volume of gas, we reduce it 1/2 by compression. The quantity of heat that the elastic fluids set free or absorb in their changes of volume has never been measured by any direct experiment, and doubtless such an experiment would be very difficult. But there exists a datum which is very nearly its equivalent. This has been furnished by the theory of sound. It deserves much confidence because of the exactness of the conditions which have led to its establishment. It consists in this. Atmospheric air should rise 1 degree centigrade when by sudden compression it experiences a reduction of volume of 1 1/116th. Footnote. Monsieur Poisson Footnote. Monsieur Poisson, to whom this figure is due, has shown that it accords very well with the result of an experiment of Messieurs Clement and Desormes on the return of air into a vacuum, or rather, into air slightly rarefied. It also accords very nearly with results found by Messieurs Gay-Lussac and Welter. See note, page 87. End footnote. Experiments on the velocity of sound having been made in air under the pressure of 760 millimeters of mercury and at the temperature of 6 degrees, it is only to these 2 circumstances that our datum has reference. We will, however, for greater facility, refer it to the temperature 0 degrees, which is nearly the same. Air compressed 1 1/116th, and thus heated 1 degree, differs from air heated directly 1 degree, only in its density. The primitive volume being supposed to be V, the compression of 1 1/116th reduces it to V minus 1 1/116th V. Direct heating under constant pressure should, according to the rule of Monsieur Gay-Lussac, increase the volume of air 1 267th above what it would be at 0 degrees. So the air is, on the one hand, reduced to the volume V minus 1 1/116th V. On the other, it is increased to V plus 1 267th V. The difference between the quantities of heat which the air possesses in both cases is evidently the quantity employed to raise it directly 1 degree. So then the quantity of heat that the air would absorb in passing from the volume V minus 1 1/116th V to the volume V plus 1 267th V is equal to that which is required to raise it 1 degree. Let us suppose now that, instead of heating 1 degree, the air subjected to a constant pressure and able to dilate freely, we enclose it within an invariable space, and that in this condition we cause it to rise 1 degree in temperature. The air thus heated 1 degree will differ from the air compressed 1 1/116th only by its 1 1/116th greater volume. So then the quantity of heat that the air would set free by a reduction of volume of 1 1/116th is equal to that which would be required to raise it 1 degree centigrade under constant volume. As the differences between the volumes V minus 1/116th V, and V plus 1/267th V are small relatively to the volumes themselves, we may regard the quantities of heat absorbed by the air in passing from the first of these volumes to the second, and from the first to the third, as sensibly proportional to the changes of volume. We are then led to the establishment of the following relation. The quantity of heat necessary to raise 1 degree air under constant pressure is to the quantity of heat necessary to raise 1 degree the same air under constant volume, in the ratio of the numbers 1/116th plus 1/267th to 1/116th, or multiplying both by 116 by 267, in the ratio of the numbers 267 plus 116 to 267. This, then, is the ratio which exists between the capacity of air for heat under constant pressure and its capacity under constant volume. If the first of these two capacities is expressed by unity, the other will be expressed by the number 267 over 267 plus 116, or very nearly 0.7. Their difference, 1 minus 0.7 or 0.3, will evidently express the quantity of heat which will produce the increase of volume in the air when it is heated 1 degree under constant pressure. According to the law of Messieurs Gay-Lussac and Dalton, this increase of volume would be the same for all other gases. According to the theory demonstrated on page 87, the heat absorbed by these equal increases of volume is the same for all the elastic fluids, which leads to the establishment of the following proposition. The difference between specific heat under constant pressure and specific heat under constant volume is the same for all gases. It should be remarked here that all the gases are considered as taken under the same pressure, atmospheric pressure, for example, and that the specific heats are also measured with reference to the volumes. It is a very easy matter now for us to prepare a table of the specific heat of gases under constant volume, from the knowledge of their specific heats under constant pressure. Here is the table. Table of the specific heat of gases. Column 1, names of gases. Column 2, specific heat under constant pressure. Column 3, specific heat at constant volume. Atmospheric air, 1. 0.7. Hydrogen gas, 0.903. 0.603. Carbonic acid, 1.258. 0.958. Oxygen, 0.976. 0.676. Nitrogen, 1. 0.7. Protoxide of nitrogen, 1.35. 1.05. Olefant gas, 1.553. 1.253. Oxide of carbon, 1.034. 0.734. The first column is the result of the direct experiments of Messieurs Delaroche and Berard on the specific heat of the gas under atmospheric pressure, and the second column is composed of the numbers of the first, diminished by 0.3. The numbers of the first column and those of the second are here referred to the same unit, to the specific heat of atmospheric air under constant pressure. The difference between each number of the first column and the corresponding number of the second being constant, the relation between these numbers should be variable. Thus, the relation between the specific heat of gases under constant pressure and the specific heat at constant volume varies in different gases. We have seen that air, when it is subjected to a sudden compression of 1/116th of its volume, rises 1 degree in temperature. The other gases, through a similar compression, should also rise in temperature. They should rise, but not equally, in inverse ratio with their specific heat at constant volume. In fact, the reduction of volume being by hypothesis always the same, the quantity of heat due to this reduction should likewise be always the same, and consequently should produce an elevation of temperature dependent only on the specific heat acquired by the gas after its compression, and evidently in inverse ratio with this specific heat. Thus we can easily form the table of the elevations of temperature of the different gases for a compression of 1/116th. Table of the elevation of temperature of gases through the effect of compression. Column 1, names of gases. Column 2, elevation of temperature for a reduction of volume of 1/116th. Atmospheric air 1. Hydrogen gas 1.16. Carbonic acid 0.73. Oxygen 1.035. Nitrogen 1. Protoxide of nitrogen 0.667. Olefiant gas 0.558. Carbonic oxide 0.955. A second compression of 1/116th of the altered volume, as we shall presently see, would also raise the temperature of these gases nearly as much as the first, but it would not be the same with a third, a fourth, a 100th such compression. The capacity of gases for heat changes with their volume. It is not unlikely that it changes also with the temperature.